In this session, we're going to discuss the topic of angles. This session is going to be a little more elementary than other sessions. I'm sure that you're already familiar with the notion of an angle because angles are used in real life. So if you're very confident in this topic, it is okay to skip this lecture or just to view various video snippets for reference. What is the unit circle? The unit circle is the circle with radius 1 and center at the center of the coordinate system. That's what unit circle means. So you're gonna hear me use the word unit circle. I'm simply referring to the most standard noble circle whose center is exactly spot on the center of the coordinate system and has radius 1. So, what is an angle? The term angle is used in real life and it is also used as a mathematical term. I want to focus our attention on the use of the word angle in mathematics. But believe it or not, the term angle is actually refers to three distinct mathematical objects that are not equivalent to one another. So, the word angle can be used to denote even more things in life, but in mathematics alone it already denotes three distinct objects. The first object is the geometric angle, formed by connecting two rays. A ray is half of a line, so a line which is but only half of it, so the other half has been discarded. So the geometric angle, so this configuration, the two rays connected together at their origin, that is a geometric angle. Next, the angle measure of such a geometric angle. I'm going to elaborate on what that angle measure is in the following slides, but for the time being, think of the arc connecting the two rays. So this blue arc here, connecting the two rays of the geometric angle. And finally, the third different meaning of the term angle is the angle measure of a rotation. That term is also used in real life. So in real life, when you say to rotate it at 180 degrees or to rotate, make a full turn, that would be rotation of 360 degrees. So that meaning of the word angle is the same as the angle measure of a rotation. Now, as you can see, angle measure of rotation, that's again denoted with an arc-like picture, but you'll notice that the angle measure of this particular rotation appears to be a picture, an arc which spans more than 360 degrees, so more than a full turn. So that's going to turn out to be the main difference between the angle measure of a geometric angle and the angle measure of a rotation. We'll elaborate on this later. All three of these terms are referred to as angles. And we as mathematicians have to use context to decide whether angle means angle formed by two rays, whether it means angle measure, or whether it means angle measure of a rotation. Except for a few introductory slides, so essentially except for the slides in this lecture, we'll take full advantage of this convention that, when we say the word angle and which of those three notions we mean, it's up to you to figure it out. So yes, that sounds a bit unpleasant, but that's how it is. Okay, now let's focus on the geometric angle. A geometric angle, or angle for short, is the figure formed by two rays called arms sharing a common endpoint called the vertex of the angle. So these two rays would be called the arms. So those are the arms of my angle. This point here, the start of the two rays, would be called the vertex of the angle. Yes, one more important thing, the rays of a geometric angle are assumed ordered. So they are not equal, they both look like rays, but one of them is declared to be the first and the other one is declared to be the second. So the ray that comes first would be called the initial arm, or sometimes people say the initial side of the angle, or the first side of the angle. And the side that comes second would be called the terminal arm, or the second arm of the angle. So this would be the terminal arm here. Which one is the initial and which one is the terminal arm is that needs to be specified. It is not clear if we do not indicate it with text or in some other way. Angle measures are depicted as arcs pointing from the initial arm of a geometric angle towards the terminal arm. So if you want to depict this angle measure, you start at the initial arm and you go towards the terminal arm. So that would be the angle measure of this geometric angle. And the angle measure is not allowed to be in this direction. So this is not the angle measure of this particular geometric angle, because in this particular geometric angle we're told that this is the initial arm and that's the terminal arm. By convention, the rays are allowed to coincide. The resulting measure of the resulting geometric angle would be called the zero angle. So that's the case when we have the terminal arm coinciding with the initial arm. A ray can be identified by its starting point and any other point on the ray. Therefore, an angle can be identified by its vertex, so that was the vertex of the angle, and one point on each of its arms. So if I pick one point on this arm, I've identified the first arm of my angle, and if I pick another point on the terminal arm of the angle, I've identified the terminal arm of the angle. So if A is the point on the first arm, different from the vertex, and B is a point on the second arm, different from the vertex, then we denote the resulting angle like this. Angle AOB, 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 angle AOB. So when handwriting angles, it is sometimes people put an arc. So if you want to handwrite angle AOB, you may put this angle sign and then put an arc through it. So that's the convention. You write an angle sign with a small arc. When typing typed texts, we do not put the arc usually, but rather we omit it. Okay, so the choice of the point A and the choice of the point B, that choice is not unique. For example, suppose that I chose point A prime on the first arm, then angle AOB would just be the identical angle as the angle A prime OB. So that would be A prime OB. Right, so these would be just identical angles. It's the same object. Now, when we write angles, the order of the letters is very important. So AO is the initial arm of the ray, and OB, the second pair of letters, is the terminal arm. And the vertex is always in the middle. So the vertex is always in the middle. So when I deal with this angle notation. Now, in the angle BOA, that angle is completely different from the angle AOB. So if I take the angle BOA, then the initial arm would be BO. So this would be the initial arm here. So if I took the angle BOA, then the initial arm and the terminal arm would be swapped. So OB would be the initial arm and the terminal arm would be OA if I were to write the letters in the opposite order. Then the angle measure would be depicted as an arc which points in the opposite direction. Once again, the angle measure of a geometric angle always points from the initial arm to the terminal arm. The two angles are, of course, the two geometric angles AOB and BOA are different. Now, I used the word geometric angle, or radian measure of a geometric angle. I already used it, and I already depicted it with this arc from the initial to the terminal arm, but I didn't tell you, I somehow used it informally. I didn't give you a formal definition of that measure of a geometric angle. Let me give you now a formal definition of an angle measure of a geometric angle. So here's how the definition goes. The magnitude of the angle measure of a geometric angle is the length of the short arc cut off by the angle from a radius 1 circle centered at the vertex. In other words, if I want, so in other words, the geometric measure, the measure of a geometric angle, that's a length, right? So that is a length which is given in the following way. You take a circle with radius 1 unit. So we take a circle of radius 1. That's my red circle. You put that circle, you center it on the vertex of the angle. So you make that circle there. And of course, the angle chops that circle into two pieces, a short arc and a long arc. The magnitude of the geometric measure of an angle is the length of the short arc, not the big one, but the length of the short arc. Whenever traversing the arc from the initial arm to the terminal results in a clockwise motion, we take the measure with negative sign, else we take it with positive. So I told you what's the magnitude of the measure of a geometric angle, but now I have to tell you whether it's a positive quantity or whether it's a negative quantity. So the convention is that if this is the initial arm and this is the terminal arm, well then, in order to go from the initial to the terminal arm along the short arc, we'd have to go clockwise, right? That's a clockwise motion. And when we're going clockwise, clockwise means negative sign. So that angle here, from here to here, would be negative. And in the opposite, if we were to move in the opposite direction, that would be positive angle. The unit of this angle is called radians, and it is denoted by rad. A circle of radius 1 has circumference 2 pi. Here's a convention. A half-turn angle is measured with pi rather than negative pi. Right? So if I'm to take the geometric angle, which is formed by gluing together two rays which lie on the same line but point in the opposite direction, then the unit circle, my unit circle, would not have the two arcs which are chopped by the unit circle would be both of length pi, and it wouldn't be clear which one is the initial and which one is the terminal arm, because it wouldn't be clear which one is the short arc. So we could either go in this direction or in that direction. So by convention, a half-turn angle is measured with pi rather than with negative pi radians. So a geometric angle is measured with a number between negative pi and pi, right? Because the short arc is never more than pi in length. So all possible geometric angles are measured with a number between negative pi and pi. Angle measures are frequently denoted by Greek letters such as alpha, beta, gamma, theta. So we often use such Greek letters to denote angle measures. Now, one more important detail. You are going to hear that that angles do not have units, right? So you're going to hear many people are going to tell you that angles do not have units. That is correct for when by angle we mean angle of rotation. So the third meaning of the word angle, that statement makes perfect sense. When we speak of a measure of a geometric angle, whether a geometric angle should be assigned units, measuring units, or not, so the measure of a geometric angle, that is actually a matter of convention, that is not fixed. So here I'm not violating any standard convention that angles are unitless, because I'm not talking about an angle of rotation, but rather about the radian measure of a geometric angle. Okay, so I'm free here to declare that measures of geometric angles do have a measurement unit, which I've called here radius. All right. And now in the previous slide, I used freely the meaning I used freely the knowledge of what's arc length. So in the previous slide, let me go back for a second. In this slide, I took that arc and I found the length of this arc, right? So I found the length of that arc, and I used that to denote the measure of a geometric angle. But what actually is the definition of an arc length, right? Because I am using that, so I'm assuming that all of you know what's the length of an arc of a circle, but have we actually covered the definition of what's the length of an arc of a circle? Well, we actually haven't. That's actually a fairly involved topic. There is a definition of arc length of an arbitrary smooth curve. So I give you an arbitrary smooth curve, something like this, and I can automatically define arc length for that curve. Okay, so there is such a definition. It is a strict mathematical definition. However, that definition may be a little bit too advanced for the exposition here. Okay, let me just give you a sneak preview of what that definition talks about. The definition states that the arc length of a smooth curve is the limit of the lengths of ever finer straight line approximations. Okay, so if I wanted to declare, if I wanted to tell you what's the length of this curve here, I'd have to take ever finer straight line approximation. So this is a 2-segment approximation of that curve. This is a 1, 2, 3, 4 segment approximation of that curve. So what I have to do is I have to take ever finer approximations of that curve. So I would have to select various points on that curve and connect them with straight lines. And what I would get is approximations of that curve. And by making them ever finer, I would get ever better approximations of the length of the curve. And taking the limit of those lengths as the number of sampling points tends to infinity, I would be getting the actual length of the curve. The details of how this is done. So what does it actually mean when I'm talking about infinitely many, the limit as the number of segments tends to infinity? What is the formal mathematical definition of the word limit? That is too advanced for the present discussion. In fact, a proper definition would require usually integrals, the notion of an integral. That is already calculus level material. So we're not going to do that in the present lecture. Okay, of course, feel free to look it up or continue in this series of lectures, and we'll get to the notion of an arc length. until we have studied integrals, we ask the reader to think of arc length as of a curve as the quantity obtained by aligning a rope along the curve and measuring the length of that rope. Now, let's cover how we measure arc lengths of circle arcs. Suppose that two circles have a common center and two different radii. So I'm having two circles with a common center. So here's the first one, here's the bigger one, right? So a small and a big circle. And the two circles have common center. So circles with common center would be called concentric circles. So I'm having two concentric circles. Okay. So let the radius of one of them be S and the radius of the other be R. Okay. Suppose we have an arbitrary geometric angle whose vertex is exactly the common center of the two circles. Suppose furthermore that angle cuts off the two circles into arcs M and L. So, of course, the angle cuts off the two circles, and so let's denote the first arc that's being cut off by our angle is M, and let's denote the second arc cut off by our angle is L. And here's the claim. So here's the statement. The ratio of the two radii is the same as the ratio of the two arcs. So if you take the arc M and you divide it by the arc L, so if you take the small arc and you divide it by the large arc, you get the same ratio as when you divide the small radius S by the large radius R. I'm not going to prove this proposition. We're going to take it as is. But let's see what that proposition implies. Let's copy, right? So here's the ratio of the radii. This is the radius S, and this is the radius R. And that ratio is the same as the ratio of the arcs. So S over R equals M over L. Now, this is true for arbitrary circles. So in particular, I'm free to choose, say, one of the two circles to have radius 1. So I'm choosing S to be equal to 1. I'm allowed to do so. It's a legal choice. There we go. S equals 1. And for purposes which are going to be apparent a minute from now, let me relabel the arc M with a Greek letter alpha. If you remember, we were using Greek letters alpha for measures of geometric angles. Okay. Next, let me massage this algebra a little bit. Let me multiply by L there, and let me multiply by R there. So L goes to the left-hand side, and R goes to the right-hand side. They swap from denominator into numerator. Okay, so I got my equality. L equals alpha times R. Now, the angle measure of a geometric angle, I want to remind you, that is the arc length cut off, not just from any circle, but from a very specific circle, from a circle of radius 1. So alpha, so this alpha here, that is an arc of a circle of radius 1. Therefore, alpha measures, so it is the measure, so alpha is the measure of a geometric angle. is the measure of a geometric angle. Whoops. Of a geometric angle. Okay. So let's take a look at the corollary. If I want to measure an arbitrary arc L of an arbitrary circle of radius that is not 1, all I need to do is I need to take the angle measure of the geometric angle, which corresponds to the length of the unit circle, and I multiply that by the radius of the circle whose arc I'm trying to measure. Once again, the arc length cut off by an angle of measure alpha from a circle of radius r equals alpha times r. So you need to take the radian measure of the arc and multiply it by the radius. In this example, we're going to exercise the formula we just learned, the formula for the arc length of a circle. Let's read the problem. Find the length of an arc of a circle whose radius is 2, and the arc is being cut off by an angle of measure 7 pi over 6. So I'm having a measure of an angle 7 pi over 6, and I'm trying to, so I'm having a circle whose radius is 2 units, and I'm trying to find the length of this curve. So I'm trying to find the length of the red curve. So let's see how that works. By the formula we just learned, the arc length of a circle is given as alpha, that's the radian measure of our angle, times the radius r. But that alpha is exactly the angle that's given to us. So alpha is exactly 7 pi over 6, and I need to multiply it by 2. 2 is the radius of the circle, and well, I guess that's it. 2 and 6, they cancel, so I'm left with 1 over 3 here, and my final answer is 7 pi over 3. So 7 pi over 3 is the arc length of that circle. The units are not specified. How did I compute this approximation here? This was by calculator. So this was calculator. So your calculator knows, so pi is approximately 3.14. So so if you use a calculator approximation for pi and you multiply by 7 and divide by 3, this is the approximate length that you get. So far, we covered 2 meanings of the term angle. And we mentioned that there are 3 meanings of that term. The third one was the measure of rotation. So now I want to focus on the third meaning of the term angle. Before that, however, I need to explain to you the meaning of the term rotation. Now, I'm sure you know from real life what rotation is, but I want to explain what's the mathematical meaning of the term rotation. In fact, the situation is a little bit unfortunate here as well. The term rotation refers to 2 distinct mathematical objects. Just like angle refers to 3 distinct mathematical objects, so the term rotation refers to 2 distinct objects. The first one is the notion of a continuous rotation. This is a gradual, with respect to time, transformation of space. What you should think of is, you should think of this point here. Here's the point B, and you should think of that point as it travels through time. So I'm assuming not only the presence of a geometric plane, but also the presence of some time, and that time is passing by, and my point B changes its position with time. So that transformation, that law of motion, would be called a rotation, a continuous rotation, or just rotation. And then there is a second meaning of the word rotation, which is an instantaneous transformation of space. So it is so whether you carry out a continuous rotation or unusual rotation or an instantaneous rotation, the end result is the same. However, when you have a non-continuous rotation, the transformation is instantaneous. There is no time. You have the point A somehow teleports, if you will, to its position point B. There is no time involved. Everything happens in the same time frame. So in mathematics, when we say rotation, without specifying whether it's continuous rotation or instantaneous rotation, so if you just say rotation without any further elaboration, we usually refer to instantaneous rotation, the teleportation kind of business. In physics, however, the term rotation most frequently refers to the continuous version of the rotation. So, and of course, in physics, often time is explicitly parametrized, usually denoted by the letter T. Whether the term rotation refers to continuous rotation or to instantaneous rotation should be inferred from context. Of course, it's possible in mathematics to use the word rotation in the same way as physicists usually do. And physicists, of course, also refer to the mathematical version of the word rotation. So the two are ambiguous. So as usual, we ask the reader to be careful when listening to these terms and to infer their meaning from context. Now let us focus our attention on the continuous rotation. A continuous rotation about a point, which is called the center of rotation, is a continuous motion of points for which the following holds. All points move in a circular fashion around the center of rotation. I'm not going to go into greater details of what that means. I'm referring to your intuition, what it means for circular rotation, for circular motion. And the distance between each rotated point and the center of rotation does not change. So the distance between this point and the center of rotation does not change. So if a point A was rotated into the point B, then the distance between O and A must be the same as the distance between O and B. These two distances must coincide. That's what the second statement means. The distance between each pair of rotated points is preserved. So if I take one pair of points, A and B, and I rotate both of them into A prime and B prime, then the distance between these 2 points, this arc, this segment here, must be exactly of the same length as that segment. So the position of a point under continuous rotation is assumed to be a function of time. So in fact, for this definition to make perfect sense, we also need to parameterize time. We need to introduce a variable for time, and that gets a little bit technical. So we're not going to do that. We're going to stop here with our definition. The trajectory of a point under continuous rotation is an arc of a circle. So a point can traverse a full circle more than once, right? So, because when we're having a continuous rotation, as time passes by, a point can revisit places which it used to visit. So I'm allowed to do this. I'm allowed to move the point B around. I'm allowed to move it around, and it's allowed to go back to where it originally was. So when we have continuous motion, it is allowed to repeat parts of arcs. We say that a continuous rotation is proper if all points under that rotation either move clockwise without ever backtracking onto themselves, or counterclockwise without ever backtracking onto themselves. So what do I mean? Well, this would be proper rotation. So this would be proper rotation. If the trajectory of a given point was like this, that would correspond to a proper rotation. This would be proper rotation. So this would be proper as well. So you can see a point made a full circle and then backtracked a bit onto itself, but without ever changing direction. And this would be non-proper rotation. So non-proper rotation would be something like this. We start onto a regular circle, but then suddenly here we change direction and we go back a little bit, and then now we go in the opposite direction. So this would be non-proper motion. Okay. The radian measure of rotation is a number with the following properties. It is a number that has sign. It could be either positive or negative. First, let's speak about the magnitude of the measure of rotation. The magnitude, so the absolute value, so the magnitude of a rotation, that's equal to the length of the arc traversed by a point under the rotation. So I'm taking an arbitrary point A, and I'm measuring the length of this arc, the arc that's traveled by A under the continuous rotation. So I'm taking the length of that arc, and I'm dividing that length by the distance between the point and the center of rotation. So this is my radius here, my number r, that's the distance between the point A and the center of rotation. So that number r, I'm dividing by it. So the radian measure of a rotation is given by taking the length, so measure of rotation, so that would be the length of the arc AB divided by the length of the radius r. So think of something like this. Say, for this particular example, we could have, think of this as something like, so an example of that would be, for example, something like a 5 centimeters arc length divided by 2 centimeters in the radius. So that would be the length of my radius, and that would be the length of my arc. Okay, so we found out the magnitude of the measure of rotation. What's its sign given by? The sign of the radian measure is taken to be negative if the rotation is clockwise, and if the rotation is counterclockwise, the magnitude of rotation is given a positive sign. So this would be given this would be a positive rotation, and if we're rotating in this direction, that would be taken with a negative sign. The radian measure does not change when we change the point whose path length we're measuring. See, in the beginning, when we started this definition, we said, well, kind of pick an arbitrary point A, right? And then with that point A, measure the length of a certain arc, measure the distance between that point A and the origin, and then divide the two numbers. Well, maybe we would have gotten a different number had we chosen a different point A. Well, the claim here is that it doesn't really matter which point you choose. If you remember, the arc length traveled by a point under rotation, it doesn't really, it is proportional to the radius, to the distance between the point and the center of rotation, right? That was that theorem about the concentric circles and the arc lengths cut off by geometric angles and out from off those concentric circles. Okay. Here's an interesting point to be made. So if I take a measure of rotation, it will be the length of a certain arc divided by the length of a certain radius. Both of them would be measured with the same measurement units. Say, for example, here I use the centimeter measurement unit. You could cancel the two measurement units. In this particular case, say, with these made-up numbers, I would have gotten something like 2.5. Now, what's the measurement unit of an angle? Well, since I cancelled the measurement unit of centimeters here and the measurement unit of centimeters there, this is unitless, no units. So it seems that angles do not have units. So radian measure of rotation has no units. But if you recall, when we're defining a measure of a geometric angle, this was given as this was a certain length, if you remember. It was given as a certain length. Length, that was a length, let me be more precise, that was the length of an arc of the unit circle. If you remember that since this was an arc of a circle, it was always between 0 and 180 degrees, right? Because we're length actually of the short arc of a short arc of a circle. Because we were always picking a short arc of a unit circle, that arc had always length less than or equal to pi measurement units. So if you can see, so a thing to note is that the measure of a geometric angle, it appears to have units. So has units, measurement units. Whereas radian measure of continuous rotation has no units. So if you hear the discussion of whether rotations or degrees have units, the answer is they both do and they don't. So if we use angles to measure rotations, you cannot speak of units. And if we use angles to measure arcs of geometric angles, you could speak of measurement units. So in other words, there are no errors. It depends on context. So whether degrees can be assigned a unit or not, it really is a matter of definition, if you wish. Okay. The radian measure of rotation equals the signed arc length traveled by a point at distance 1 from the center. Right, because if you take the distance between the point A and the origin O to be equal to 1, then if you take the length of AB, and you have to divide it by the length of R, but that's the length of the arc AB divided by 1, because we have selected R to be equal to 1. So we're getting simply, when we divide something by 1, we're getting simply the length of the arc AB without the units. The units have cancelled. So this one had units here, this one had the units as well. So here I've omitted the units, but if there were units, I would be cancelling the units here. Okay. So in that way, since a circle of radius 1 has circumference 2 pi, a full counterclockwise turn is measured by 2 pi radians. So a full counterclockwise turn is 2 pi radians. In this slide, we're going to discuss the question of when are two angles equal or equivalent. Now, this question actually really depends on which of the three meanings of the word angle we are actually using. So, if we use the meaning of the word angle, which is a geometric angle, then two angles are equal if they literally coincide. If we speak of their angle measures, that no longer needs to be the case. Right, because they're angle measures, these are numbers, and two numbers can be equal without you having the exact same configuration of a point and two rays. So to avoid the ambiguity of whether two angles that have the same measure are actually equal or not, we're going to introduce the term congruent. So we're going to introduce the term congruent. So two geometric angles are congruent, or if you wish equivalent, if they can be transformed one onto the other with a sequence of translations and rotations. So here are two angles. The way I've depicted them, they appear to have the same angle measure. So if you take that arc and you measure the length of the arc of the unit circle chopped off by this angle, you do the same with that angle, you're going to find that this arc here equals that arc. Okay, so the measures of these two angles are the same. Now, by definition, those two angles would be the same by this technical definition that we've given here. So those two angles would be congruent or equivalent if I can transform one onto the other with a sequence of translations, such as this one. So, of course, if the two angles are to be transformed into one another, their vertices must coincide. So here we go. I can transform one angle onto the other by pushing the vertex of one angle onto the vertex of the other, and then I'm also allowed to do a series of continuous rotations. There we go. And I have now transformed the first angle onto the second one. So that I demonstrated on a picture. But you're going to say, well, in the beginning you told us that the two angles were kind of equal because their angle measures are equal. So how does the notion of two angle measures being equal, so two lengths of arcs being equal, so how does that compare to this notion of equivalent angles? Well, the answer is the following. Two geometric angles are congruent if and only if they have equal angle measures. So whenever you give me two angles and their angle measures coincide, I can move one angle onto the other by translation and rotation. In fact, I showed you how to do it. You first translate the vertex of one to meet the vertex of the other, and then you rotate. Recall that the term angle refers to both geometric angle, which is the configuration of rays in a center, and their angle measure. And whether the word angle, which of the two distinct objects we're talking about, that really depends on context. So in other words, it's not specified. It's up to you as intelligent human beings to discern what I mean when I say the word angle. Do I mean geometric angle or the angle measure of such an angle? So in other words, if you hear a mathematician or non-mathematician say, well, these two angles are equal, however, you see that the angles are in two different positions in space, so they clearly do not coincide, they don't have the same rays and the same origins. So if you hear a person say, well, these two angles are equal, but they literally are not the same configuration, then you have to interpret their words as if they said that their two angle measures are equal. Or you have to interpret their words as if they said, I could take one of the angles and I could move it on top of the other angle with a series of translations and notations. Or in other words, the two geometric angles are congruent. So when you hear people talk of equal angles, they either mean congruent geometric angles or equal angle measures of two geometric angles. In this slide, we're going to discuss the relationship between angles in the coordinate system. Suppose I've given you an angle measure. Since this is a measure of a geometric angle, it's a length of a short arc of the unit circle, so it's a number between negative pi and pi. Now there are infinitely many geometric angles that have that measure. Just take any angle with that measure and just move it around and rotate it around in the plane, and you have infinitely many congruent angles with the same measure. Okay, but is there a best way of selecting one particular representative, one particular angle with a given measure? And the answer is yes. Now, of course, by saying best way, I mean best way relative to the choice of the coordinate system. So suppose we have first fixed a choice of a coordinate system in our plane. How that choice is made, that's a different discussion. So we postpone that, leave that to the side. Somebody has made that choice. We have. Now, this means that there is one point, namely the center of the coordinate system, which is preferred. That's a point which is somehow distinguished among all points. So what we do when we want to choose a geometric angle with a given measure is we choose the best possible point for its vertex, namely the origin. Right? We have a distinguished point, that's the origin of the coordinate system, and every angle has a distinguished point as well, so it makes perfect sense to select the origin to be the angle's vertex. So that's, you could argue, the best choice you could take. The next thing you do is you need to select the initial arm of your geometric angle. What you do is you always select the x-axis to be your initial arm. And in the positive direction, not the negative x-axis, the x-axis in the positive direction. You always select that one to be the initial arm, right? Because to fix a coordinate system, you need to select an origin and you need to fix the direction of the x-axis. And so that's the most natural ray, if you will, is the first ray of the coordinate system, the x-axis. Okay, so now I've told you how to select the vertex and the initial arm. Now how do we construct the terminal arm? Once we have selected the vertex and the initial arm, if we know the angle measure of the angle, which we do in this case, that's the number alpha, then we have no longer any choice for the position of the initial arm. It is a function of of the choices we have made so far. So what we do to construct the terminal arm, the second arm of our angles. This is the first arm, this is our initial arm. So what we do is we take this point, the point with coordinates 1, 0, that point, and we rotate it along a circle whose center is at the center of the coordinate system. We go counterclockwise if alpha is positive, and we go clockwise if alpha is negative. And the amount of distance we travel on that circle is given by the absolute value of the angle. So here, the distance that you see here is given by the absolute value of alpha. Think about it. Such a system could actually be constructed in the physical world. So in the physical world, you could actually fix a pivot, make a solid connection between this point and the center of coordinate system, say with some rigid rod or something of the sort, and then you could actually rotate. While rotating, you could measure distance, say by by dropping a rope or some other means. And so you could actually physically implement what we're showing here. So you could actually physically move a given distance. And the amount of distance we travel is alpha units. Then what we do is, we took that point, we traveled for alpha units along a circle, and we arrived at another point, and that point we use to select the terminal arm of our angle. So we use that point and we connect it to the origin, and then the ray formed in this process, pointing from the origin to that point, so that ray is the terminal arm of our angle. Now, notice that at the start, this construction appears to work only for a geometric angle, right? We started with a geometric angle. So we started with an angle measure, which was between negative pi and pi. So this number alpha was between negative pi and pi. But everything that we did, so we fixed a point and then we traveled a given distance. Okay, so everything that we did here could be carried out if the amount of distance traveled is bigger than pi units. So in this case, this would be pi units of travel distance, and I could travel on the other side as well. So the construction extends in a straightforward fashion for angle measures which are greater than pi radians or smaller than negative pi radians. Right, I could do more than 2 pi radians as well. In this way, for every real number alpha, we can assign a geometric angle. If the starting number was in the interval from negative pi to pi, the so obtained geometric angle does have the same measure as that original number alpha. But if the measure alpha was not in that nice interval, the measure of the geometric angle obtained by this construction will be different will be different. So the measure of the geometric angle will be different from the original number alpha, right? So if I started with if alpha was in the beginning 1 radian, and then I started with another alpha prime, which is 1 radian plus 2 pi. Well, so I would get again the same point, so I would get the same geometric angle. But the two numbers from which I started would be different. So if you wish, the assignment from an angle measure to a geometric angle is not one-to-one. It is possible to have two different angle measures which result in the same geometric angle. How is that possible? Well, just take one angle measure and add 2 pi units to it. Okay? Whatever you do, however, the only way for you to have the same geometric angle obtained by two different angle measures is to have those two angle measures differ by a multiple of 2 pi. So by an even multiple of pi. So if alpha and alpha prime result in same geometric angle, that means that their difference, alpha minus alpha prime, must be a multiple of 2 pi. Or a multiple of 2 pi, that's the same thing as saying an even multiple of pi. Okay? In this slide, we're going to discuss degrees and radians. Degrees is a unit for measuring angles, which we denote by this circle symbol. The relationship between degrees and radians is the following. If you take pi radians, that is the same thing as 180 degrees. So pi radians is 180 degrees. By the way, I want to point your attention to the fact that, to the word unit. Please do not be scared by that word. So we already discussed that radians are themselves either have units or not, or they don't have units, depending on your definition, depending on your viewpoint, whether you mean angles as measures of rotations, those have no units, and whether you mean angles as measures of geometric angles, those, it's a matter of definition there, but the more natural choice would be that they do have units. Okay. So please do not be scared by this word unit. This word unit is to be interpreted as the relationship between radians and degrees, and whether degrees are have units or are unitless. That depends on whether the radians themselves are given to have units or not, are assumed to have units or not, which once again we already specified that is a matter of definition. So please ignore this word unit. It is just, so I'm using the word unit here not as a technical mathematical term or a technical term from physics. I'm using it as an English language reference to the fact that radians are connected to degrees. Okay, so the relationship between degrees and radians, that relationship is the following. Pi radians is the same thing as 180 degrees. In other words, what does this mean? Well, if you remember pi radians, that was, what was that? If you take a circle of, so take a circle of radius 1, take a circle of radius 1 unit, and pi radians corresponds to a rotation which is given by traveling along that unit circle a distance of pi units. And of course, the full circle has circumference 2 pi, so half of, so traveling pi units on the unit circle corresponds exactly to traversing half of the unit circle. So a half turn is measured by pi radians. But that is the same as saying, but we know from practical experience, so we know degrees, of course, from real life. I know that you know what degrees are from real life, and you also know from your practical use of the word degrees that 180 degrees is also the measure of a half turn. So pi radians is the same as a half turn, which is the same as 180 degrees. Now, if we divide both sides of this equality by pi, so I'm taking pi downstairs there, that means that 1 radian is equal to 180 degrees divided by pi. Now, pi is approximately 3.14. So if you take 180 degrees and you divide it by 3.14, you're going to approximately get, this is a decimal approximation, 57.3 degrees. So if people say 1 radian, that is about 57 degrees, give or take some error. Okay. Now, I've seen this conversion very, very frequently, so frequently encountered. So it is actually worth to remember that 1 radians is about 57 degrees. So what you want to do is you want to remember that pi radians is 180 degrees, and every time you need to know what 1 radian is. The best thing you should do is take the number 180 and divide it by pi. Usually you can do that on your calculator. Usually your calculator is going to have the constant pi built in if it's a scientific calculator. So you just type in 180, you divide it by pi, and then you get a numerical approximation for 1 radian. Now, the opposite conversion from going from degrees to radians, from 1 degree to radians, that's less frequently used. Specifically, one degree, using the fact that that's about 0.017 radians, I've never had to use that in practice. So these conversions are very frequently used. Degrees are useful because the most frequently encountered fractions of a half-turn are measured by a whole number of degrees. So the most frequent fractions of a half-turn would be a quarter of a turn, or a sixth of a turn, or a twelfth of a turn. So those would be an integer number of degrees. A tenth of a turn would also be an integer number, an integer amount of degrees. That is very, very useful. If a measurement unit is not specified, it is implied to be radians. So if you see an expression like this one, sine of 5, since there is no circle next to the number 5, the number 5 stands for 5 radians. So if you see sine of 5, that is sine of 5 radians. If we want to say sine of 5 degrees, we have to spell out the degrees. So we have to explicitly write the degrees. If they are not written, then it is assumed that they are measured in radians. Now, this is the mathematical convention. Other places do not follow that convention. So there are important pieces of software in which when you write a number, it is assumed to denote angle. So when you write a number to denote an angle, it is assumed to be written in degrees. So the degrees are default. They are the default. They are for example, in PostScript. So PostScript. So that's the PDF format. So PDF format. So these particular slides all the graphics in these slides were programmed in PostScript, and in that programming language, if you write sine of 5, it is assumed to be sine of 5 degrees. So if you wish, the programming language PostScript does not follow this convention. So this convention is math only. So if you're outside of the realm of math, so if you are in a particular programming language, this convention may not hold. You have to look it up. But don't think that only in math we assume the default to be radians. For example, in one of the most popular programming languages in the world, so in JavaScript, the default measurement unit is radians. So radians default in JavaScript. So this is a popular programming language. Popular programming language. In other words, the programming language in which PDF files are written. If you've ever opened a PDF file, you have been a user of that programming language. So one of the great programming languages, PostScript, uses by default degrees. Another great programming language, the JavaScript, that's the programming language which runs inside the web browser. That perhaps some people claim that that's the most popular programming language in the world. Well, that one uses radians. So both conventions are super useful and super used in practice. And which one is the default? Look it up. Always look it up. In this slide, we're going to make a very quick exercise on the conversions from degrees to radians. Let's go. So what I'm giving you here is I'm giving you an angle in degrees. So I'm going to be giving you an angle in degrees. And down here, I want you to give me the angle in radians. And then we're going to go the other way around. First, I'm going to give you radians, and I'm going to ask you for the degrees. Okay. So, 45 degrees. How many radians are 45 degrees? Sure, you guessed it correctly. Pi over 4 radians. So, let's see. In order to go from 45 degrees, so in order to go from 45 degrees to radians, I need to use this formula. So 45 degrees is the same thing as the number 45 without the circle, divided by the number 180. So I've removed the circle and I've put the number t upstairs, and then I'm multiplying that by pi. So 45 divided by 180, that happens to be 1/4 times pi. All right, if you take 180 and you divide it by 45, you're going to get, well, I guess you're going to get 4. And 4 times 5 is 0, carry over 2, well, I guess 80. So 45 divided by 180 is 1 divided by 4. Okay. So 36 degrees. How many radians are 36 degrees equal to? I'm sure you guessed it correctly. 36 degrees are exactly 1/5 of 180 degrees, right? If I take 5 and I multiply it by 36, I'm getting 5 times 30 plus 5 times 6. So I'm getting 150 plus 30, so I'm getting 180. So if you take, so 36 degrees is the same thing as 36 divided by 180 times pi, which is 1/5, because 5 times 36 is 180. So 36 divided by 180 is 1/5 times pi. So 1/5 of pi radians, pi over 5 radians. Negative 20 degrees, what's that equal to? I'm sure you guessed it correctly. That is negative pi over 9. Why is that the case? Well, you take just negative 20 and you divide it by 180. The 0 cancels. 2 divided by 18 is 1 divided by 9 times pi. So 1 minus 1/9 pi. Whoops. Let me work it out from the beginning. Negative 20 degrees is the same thing as negative 20 divided by 180 times pi, which is here 0 cancel, the 2 cancels, 2 and 9 and 1 on top, so we get minus 1/9 times pi, or what is the same, minus pi over 9. 360 degrees, how many radians? 2 pi. Negative 720 degrees, how many radians? Negative 4 pi. Minus 225 degrees, how many radians? Let's see. 180 degrees plus 45 degrees is 225 degrees. This was pi radians we mentioned. 45 degrees is pi over 4 radians. So these two must be equal to pi plus pi over 4 radians. So these must be equal to 5 pi over 4. So, and there's a minus sign in the front, so the answer should be negative 5 pi over 4. Correct, negative 5 pi over 4. 2015 degrees, how many radians is that? Well, I guess we need to take 2015 and we need to divide it by 180 and we need to multiply that by pi, right? So I need to take 2015 divided by 180. What do I get? First I'm having 180 here, subtract, I'm getting 21. 215 divided by 180, that is 1. So minus, minus 180, and I'm left with that is 35 for 35 degrees if I'm not mistaken. So let me carry it out over here. Once again, I want to repeat the computations. 180, 2015. So I'm dividing 2015 by 180. I'm getting 1. Subtract the 2, I'm getting 21. Okay, pull the 5 downstairs. I'm getting 1, and 180 there. I subtract the 2, 15 and 20, that is 35. So I'm getting 11 times 180 degrees plus 35. Right? So that is 11 times 180 plus 35 divided by 180, whole thing times pi. So that is 11 plus 35 divided by 180 times pi. So 35 here you can cancel out a factor of 5, you're left with 36. So I guess in the end you get 11 times 36 plus 7 over 36. So what's that equal to? 11 times 36 is, well, I guess 36 and 36. So 396. You add 7, you get, so 396 plus 7 over 36. So our final answer is 403 over 36 times pi. Whoops, pi went missing. 403/36 pi. All right. Now let's convert from radians to degrees. So if I start with pi over 3 radians, how many degrees is that? Now that is how many degrees is pi over 3 radians? Sure, you guessed it correctly, 60 degrees, right? Because if pi is 180 degrees, then pi over 3 is 180 degrees divided by 3, which is 60 degrees. 180 divided by 3 is 60. Pi over 10, how many degrees? I'm sure you guessed it correctly. 18 degrees, right? Because if pi is 180 degrees, then pi over 10 is 180 degrees divided by 10, which is 18 degrees. I'm using that formula here. 11 pi over 6. How many degrees is that? I'm sure you guessed it correctly. So pi over 6, that is 180 degrees divided by 6, which is 30 degrees. So if you take 11 times pi over 6, that is 30 degrees times 11, which happens to be 330 degrees. So 330 degrees. 7 pi over 4, what's that equal to? I'm sure you guessed it correctly. It's equal to, well, let's see. 7 pi over 4 is certainly equal to 8 pi minus pi over 4. I've represented 7 as 7 pi, I've represented as 8 pi minus pi. So that is 8 pi over 4 minus pi over 4, which is 2 pi minus pi over 4. Now pi over 4, if you remember, that was 45 degrees. And 2 pi, that was 360 degrees. So what we have is 360 degrees minus 45 degrees. So what we get is 315 degrees. Pi over 7. How many degrees is that? I was pulling your leg. This is a bit of a tricky question. It's 180 divided by 7 degrees. And this is not an exact division, so you can't really simplify it. It's 180 divided by 7 degrees. If you will, if you have a calculator handy, you can compute a numerical approximation. It's about 25.7 degrees. But once again, this was a tricky question. I wasn't really expecting an answer. 180 divided by 7 degrees. That's not a real answer because I haven't truly computed anything here. 13 pi over 6, how many degrees is that? Well, let's see. That's, I guess that's 11 pi over 6 plus a third of pi, right? So it should be 390 degrees, is it? Let's see. 13 6 of pi is equal to 12 plus 1 over 6 times pi, which is 12 6 plus 1 6 times pi, which is 2 plus 1 6 pi, which equals, well, it equals 2 pi plus pi over 6. We already mentioned that 2 pi is 360 degrees, and to that you add pi over 6. Well, we did compute that pi over 6 was 180 degrees divided by 6, so that's 30 degrees. So pi over 6 is 30 degrees. And 360 degrees plus 30 degrees is 390 degrees. There we go. Minus 5 pi over 4. Sure, you guessed it correctly. That was actually very easy. That's minus 225 degrees. Why? Because we did it before. So negative 5 pi over 4 was negative 225 degrees in the previous conversion. So, okay, I cheated. How I should have done is negative 5 pi over 4, that is equal to negative 4 pi over 4 minus pi over 4, which is minus pi over 4, which is minus 180 degrees, minus 45 degrees, which is minus 225 degrees. But then again, I didn't really need to do that because I could just cheat in the, because we already did this in the preceding example. And finally, 2 radians, what amount of degrees is that? Okay, this is a tricky question. So if we were to follow the formula, we need to use 2 radians, and so if pi radians are 180 degrees, so in order to get to pi, you'd have to divide here by pi, and you'd have to multiply by 2 if you want to get to 2 radians, right? So the number 2 is 2 times pi over pi, so it's 180 degrees divided by pi, so it's 180 degrees, 2 pis of it, right? So 2 divided by pi, this proportion, and that's not really a nice number, right? So that's approximately 180 degrees times 2 divided by 3.14, right? So pi is approximately 3.14. So, and you can approximate that with a calculator. It turns out this is 2 radians. Remember, 1 radian was approximately 57 degrees. So 2 radians are approximately 114 degrees, right? So just a reminder, 1 radian was approximately 57.3 degrees. So 2 radians is approximately this. We already saw such a problem in a preceding example. So the problem goes like this. Find the length of an arc of a circle of radius 3 units, so this is the radius, cut off by an angle of measure 230 degrees. The only twist is that in the preceding time when we were solving this problem type, the arc of the circle was measured in radians. So the preceding time when we were solving this, previous time when we were solving a similar problem, arc was given in radians. So the only difference between this problem and the preceding one is that now our arc is in degrees. So that's the only novelty in this particular problem. So how is this problem solved? Well, this is actually a very simple problem. All you need to do is remind yourself that the arc length of an arc, part of a circle, is equal to the angle, the length of the angle times the radius. So in this case, in this case, the radius r is 3, because that's given to us, and what's the angle? So what's the angle equal to? So that's the angle alpha. That's the 230 degrees. What's the angle equal to? Now, if you remember this arc length formula, this was angle in radians, right? This was the angle in radians here. So you cannot substitute the number 230 degrees in there directly because it's not in radians. So what do? If alpha equals 230 degrees, now if you multiply by pi and divide by 180 degrees, right, you're going to get, well, you're going to convert to radians. So 230 degrees, well, pi radians is the same thing as 180 degrees. So if you multiply by pi radians divided by 180 degrees, you're really multiplying by 1. So you're not changing the expression. So 230 degrees is the same thing as 230 degrees times pi radians divided by 180. And that's it. The 0 cancels here. You can cancel a 0. 23 18ths, you can't really be simplified. So there it is. For the number alpha, you need to fill in the number 23 18ths pi. And that's it. 3 18ths, that's 1/6. 18 divided by 3 is 6. So we get 23 pi over 6. And that's the final answer to our problem. If you possess a calculator, you can, so this is a numerical approximation of that length. So if this is an actual physical quantity that you care about, not just a problem you're solving for an exam, you may want to approximate that number with your calculator. In this slide, we're going to quickly review the most frequently encountered angles. We need to have those angles memorized for the practical purpose of exam taking, if we're in a phase of life when we're taking exams. It may also be a good technical skill to have in some particular areas of activity. For example, if you're generating mathematical graphics and you're programming them in PostScript, memorizing these angles comes in handy. So I'm personally using these angles myself for my work, but you do not need to have them memorized if you're not going to have an exam coming soon. However, if you are having an exam soon, please memorize these angles. Okay, so now what we're going to do is I'm going to ask you quickly, I'm going to give you a certain amount of degrees, and I'm going to quickly ask you for corresponding radians. And once again, please, if you're going to be soon taking an exam, memorize those. So 0 degrees in radians, I'm sure you guessed it correctly, 0 radians. 30 degrees in radians, pi over 6, I'm sure you guessed it correctly. 45 degrees in radians, sure you guessed it correctly, pi over 4. 60 degrees in radians, sure you guessed it correctly, a third of pi. 90 degrees in radians, that's this angle, that's the right angle, right? A right angle in radians, sure you guessed it correctly, that's half of pi. 120 degrees in radians, I'm sure you guessed it correctly, 2/3 of pi. 135 degrees in radians, that's this angle here. 135 degrees in radians, I'm sure you guessed it correctly, 3/4 of pi. 150 degrees in radians. I'm sure you guessed it correctly, that's 5/6 of pi. 180 degrees in radians. Pi, I'm sure you guessed it correctly. 270 degrees in radians. I'm sure you guessed it correctly, 3/2 of pi, or 1.5 times pi. And these may be also useful to memorize. 210 degrees is 7/6 of pi, 225 degrees is 5/4 of pi, and 240 degrees is 4/3 pi. 360 degrees, what's that equal to? I'm sure you know this, that's 2 pi. And once again, it may be useful to memorize these. 5/3 pi is 300 degrees, 7/4 pi is 315 degrees, and 11/6 pi is 330 degrees. Integer quantities of radians are not rational multiples of 180 degrees of a half term. So they're not easy to compute with. So 1 radian, just to remind you, 1 radian, well, 1 radian, so let's see, pi radians is 180 degrees. So 1 radian is 180 degrees divided by pi. So that turns out to be about 57 degrees. 2 radians, that is 2 times 180 divided by pi. Here's 3 radians. So 3 radians, that's less than 3.14 radians, which is pi, which is 180 degrees, this is approximately pi. So this number here must come before a half a term. Here are 4 radians, here are 5 radians. 6 radians, that must be before a full term, because 6 is less than 3.14 times 2. So 6 radians must be less than a full term. And here's 7 radians, here's 8 radians, and so on. This goes on for a while. Now notice that since all of these, since an integer number of radians is not a rational number of degrees, these marks here, they'll never repeat. So we'll never visit if we start marking off integer amount of radians on the circle, on the unit circle, we'll never visit the same place again. So these marks will never hit in the exact same spot. So that hints to the difficulties, to the numerical difficulties of computing with radians. For example, if you want to determine in which quadrant a given amount of radians lies, this is not so easy to do, because think about it. If I ask you 8 radians, in which quadrant it lies, you need to first convert it to degrees, and then look between what multiple of 90 degrees that amount of degrees lies, right? So you see that 8 radians, that is about 458 degrees, and 458 degrees happens to be bigger than 450 degrees. That's 5 times 90 degrees, and it's less than 6 times 90 degrees. So for you to tell me in which quadrant does 458 degrees lie, you need to fit 458 degrees between multiples of 90 degrees. Now that's easy to do if you know the numerical value of given amount of degrees, but if I give you 8 radians and ask you how many degrees is that, what you need to do is you need to take 8 radians, okay, and that was 8, so that is 8 divided by pi times 180 degrees, right? And now to actually compute that, you need to know pi. So if you want to compute want to compute to that. Of course, you could use a calculator, but your calculator is very powerful. It does a lot of computations. So if you want to compute this number without a calculator, you need to know the number pi with a great precision. So need to know pi, it's 3.1415, so on, right? So you need to know many digits after the decimal point in a numerical approximation for pi. So, when trying, say, to figure out if I give you a given number of radians, in which quadrant that the corresponding angle lies, you are going to run into issues of numerical computation. To anybody who disagrees with that, I propose the following problem. Take 2017 radians and figure out in which quadrant do 2017 radians lie without using a calculator. To anybody who thinks that this is an easy problem. Yes, why 2017? Because I'm shooting this video in the year of 2017. So once again, dealing with radians is naturally uncomfortable due to the numerical errors introduced by the number pi not being rational, and by the fact that every time you compute with the number pi, you need to introduce numerical approximations for the number pi. In this slide, we're going to cover the notion of coterminal angles. If you remember, a few slides ago, we studied how given an angle measure, how to construct a geometric angle. Right, so from a given angle measure, how to make a geometric angle. So just quick recap of that, of how that worked. We selected the vertex of the geometric angle to be the center of the coordinate system. We aligned the initial arm onto the x-axis. Then we took the point with coordinates 1, 0. Then we used the angle measure to travel a given distance using a given angle. Then we took that point and we used that second point to construct the terminal arm of our angle. So this is how we construct a given geometric angle from an angle measure. But if you recall, that construction was not unique, so it was possible to take two different angle measures and arrive at the same geometric angle. So the geometric angle was the configuration of the two rays. So how was that possible? Well, like this. If you take this angle here, that would be, in this case, I drew the second angle was the angle alpha plus 2 pi. So alpha plus 360 degrees. So if you do that, you're going to get the same geometric angle. So two angles are called coterminal if the corresponding geometric angles are the same, literally coincide. They have the same initial and terminal sides. So here we have to be super careful in distinguishing the two completely distinct and different uses of the word angle. So we were using once the word angle to measure the measure of an angle, and once we're using the word angle to denote a geometric angle. So once again, a geometric angle was a configuration of two rays and a vertex, and an angle measure was just a number. Okay. How can that happen? So here I've drawn a bunch of coterminal angles for you. So here's one angle, but you could take rather than using that angle, you can travel in the negative direction. There you go. Or you could take one angle and come around multiple times. So the set of angles coterminal with a fixed angle alpha consists of all angles obtained in the following fashion. So suppose I'm giving you an angle alpha and I'm asking you, find me all the coterminal angles. All you need to do is form form all numbers of this form. So here's the number alpha. I gave you number alpha. And then if you want to find all the coterminal angles, what you need to do is add all possible even multiples of pi. So take the number alpha and add all possible even multiples of pi. So 2k here is an integer. So k is an integer. So 2k is an even integer. So you take alpha, and to alpha you add an even multiple of pi. So you add all possible even multiples of pi to the number alpha, and you obtain the entire set of coterminal angles. In other words, what you need to do is you take the number alpha, you write it there, and besides that number alpha, you take the number alpha plus 2 pi, then alpha plus 4 pi, then you write alpha plus 6 pi, and so on all the way to infinity. Alpha plus 8 pi. Of course, you don't write infinitely many numbers. After some point, you write dot, dot, dot. And same in the opposite direction. You write alpha minus 2 pi, then alpha minus 4 pi, then alpha minus 6 pi. If you wish, we can include a few extra, alpha minus 8 pi, and so on, all the way to infinity. Of course, you don't write infinitely many numbers. You write dot, dot, dot. In this example, we're going to quickly exercise the notion of coterminal angles. Let's read the problem. Find all angles that are coterminal to pi over 4. Next problem, find all angles between negative 2 pi and pi that are coterminal to pi over 4. So just a reminder, so two angles, so angles are coterminal, so coterminal angles was the angles are different. Their difference is multiple by multiple, integer multiple of 2 pi. Okay, so an even multiple of pi. Once again, the terminology for coterminal angles was such because two angles were coterminal if and only if their corresponding geometric angles coincided. Okay, so let's find all angles that are coterminal to pi over 4. That really is a piece of cake problem by the theory that we just studied. All angles coterminal with pi over 4 are all angles of the form pi over 4 plus 2k pi. Here k is an integer. So this k is an integer, so 2 times k is an even number. So if I write 2 times, so every even number can be written as 2 times an integer. So this gives me this. So this gives me the set of all angles which differ from pi over 4 by an even multiple of pi. Now, the real problem here is the second part of the problem. So here's what we're really being asked to do. Among all of these numbers, we're asked to find those that happen to be in the interval between negative 2 pi to pi. So how do we do that? Here's a procedure which is fail-safe for an exam. So what I'm trying to teach you right now is not some algorithm how to write a program to do that, or I'm not trying to teach you a recipe that could be that is a part of a mathematical proof. I'm trying to give you a practical skill for listing the numbers among those infinitely many numbers, the finitely many that happen to be in this interval. So I'm trying to give you a practical procedure for listing them in an exam setting. So here's what you do. You write the numbers in an infinite list. So in the middle, you write the number pi over 4. And then you write pi over 4 minus 2 pi. So here we're having the number k equal to 0. Here we're having the number k equal to 1, and so 2k is negative 2. Here we're having 2k equal to negative 4, so this corresponds to k equal to negative 2. Here we're having k equal to 1, which corresponds to, well, if k is equal to 1, then 2 times 1 is 2k, and here we're having k equal to 2. So what you do is the following. You take your starting angle, and then you copy that angle multiple times, and then you start subtracting even multiples of pi and adding even multiples of pi. How many should you write? The rule is the following. Write as many terms of this infinite sequence to the right, so that you pass the number pi. So ensure that the last number you wrote, so the rightmost number, so ensure that this rightmost number, so ensure that the last number is greater than pi, is greater than this number. Okay, so if you want to find all angles in that particular interval, you start listing all coterminal angles until the angles you have listed surpass the number pi. You can also go beyond that. So if you don't want to think very, very hard of, well, how does exactly pi compare to pi over 4 plus 2 pi or pi over 4 plus 4 pi, you can just write many, many terms until you're absolutely sure without any computation that the number you have written here is bigger than the number that you see there. Same story to the left. So to the left, you make sure that leftmost number is smaller than the left end point of the interval in which you want to fit all of your coterminal angles. Now, once again, it is okay to go. It is okay to write extra terms to the left. You need to go to the left of negative 2 pi, but you can go even further to the left. So if you're not sure how pi over 4 minus negative 4 pi compares with negative 2 pi, just subtract another 2 pi. So write as many terms as your heart desires. Okay, so now that you have done that, what you do next is you compute these numbers. So you compute actual values here. You can add them as fractions, or if you can, maybe not, you don't need to write, you can compute them in your head, and you compare your computations with the numbers pi and negative 2 pi. And what you do is you cross out those terms that do not lie in the interval that was indicated in the problem. So this particular problem asks us to find all angles between negative 2 pi and pi. So pi over 4 plus 2 pi, that's clearly bigger than, so this number is clearly bigger than 2 pi, because it's just, and that's clearly bigger than pi. So that number is outside of this interval. This number is even larger, so we have to cross it out. And by the same token, all numbers in these infinite dots, they have to be crossed out. Now pi over 4, that is less than pi, and it's actually a positive number, so it's bigger than negative 2 pi. So that one, we shouldn't cross it. This number here, we shouldn't cross it either, because it is negative 2 pi plus something positive. So it's automatically greater than negative 2 pi. And it still is negative, because pi over 4 is much smaller than 2 pi. So that's still less than pi. So that number here is between negative 2 pi and pi. And finally, this number here, that is less than negative 2 pi. So this is less than negative 2 pi. Why? Well, because pi over 4 minus 4 pi is certainly equal to, let's see, well, I guess it's negative 3 pi minus 3/4 of pi, which is definitely less than negative 2 pi, right? Because you add pi to this, and this is less than that, and you can just forget about that term. So we need to cross that term, and by the same token, all terms to the left of the first term on the left we crossed, they also get crossed out. And that's our final answer. These are the two angles coterminal with a starting number pi over 4. So these are the two angles that lie in the interval between negative 2 pi and pi. So our final answer is pi over 4, and pi over 4 minus 2 pi. That happens to, if you compute it, you will see that you can compute that to negative 7 pi over 4. Now, I want to point out something. At first glance, this procedure looks deceptively easy. However, this procedure will arise as one step of solving a much more complicated trigonometric equation problem. So later on, we will study tricky trigonometric equations. And so we're going to have to do a lot of steps to solve these problems, but at some point, we will boil down that difficult trigonometric problem to the problem of finding all angles coterminal with a given angle within a certain interval. And when that happens, sometime in the future, this procedure will be coming very, very handy. Something more. This procedure, it looks deceptively easy, but in the context of that future problem type that you're going to see later, so in the context of that future problem type, this technique is not going to be so easy. And if you have not exercised yourself on this technique, you may find some aspects of trigonometric problems to be quite difficult. So please try to exercise this procedure, and I highly recommend using this method of writing, of listing numbers and crossing them out as a practical tool, for doing things efficiently in an exam setting. Two positive angles are called complementary when they sum to a right angle. So an angle of measure 90 degrees. So two positive angles. So the angles must be positive, and they must sum to 90 degrees. So each of them must be smaller than 90 degrees, right? Because both of them are positive quantities. So you need to have something like 45 degrees plus 45 degrees equal to 90 degrees. So these two would be complementary. So the angle 45 degrees would be complementary to itself. Complementary. Or 60 degrees and 30 degrees, those would be complementary. So complementary angles are a useful tool for computing trigonometric functions later on. So that's what complementary angles are used for. What are supplementary angles? That's again another terminology which is to be used later on when we start dealing with trigonometry. So for now, let's just study the terminology as is. Two positive angles are called supplementary when they sum to 180 degrees. So something like 30 degrees and 150 degrees. So the sum of those two angles is 180 degrees. So these would be called supplementary. These would be supplementary angles. And things like that don't count. So 210 degrees plus minus 30 degrees, that's again equal to 180 degrees, but these are not supplementary angles because the angles have got to be positive. So this would be not supplementary angles because this angle is negative. Okay, that is just terminology. If you ever forget, if you ever see the word complementary or supplementary and you don't quite remember what that was, please revisit the old slides. One final piece of theory. I want to cover the formula for an area of a circle sector. What is a circle sector? A circle sector is a figure which looks like this. Think of it as a pizza slice. So if a circle is a pizza, then a circle sector will be a pizza slice. What is that pizza slice parameterized by? It's parameterized by an angle alpha. That gives the angle of the slice, and of course, r parameterizes the radius of our circle. So, of course, the formula for an area of a sector is given here, but I want, rather than reading that formula for you, I want to naturally reason what that formula is below. So I want to tell you why the formula is the way it is, and in the process, hopefully, you'll memorize that formula. So first of all, I want to start with area of full circle. What's the area of the full circle of radius r? Sure you guessed it correctly. The formula is pi r squared. Next. It seems that, so the full circle corresponds to a sector of size 2 pi, right? Because if you take 2 pi, you're taking a full turn, so you're just taking a slice which corresponds to the whole pizza. So the full circle is given by an angle of 2 pi. So it seems that if A is the sector area, then the percent of the total area, percent of full circle, taken by the sector A is given by the ratio of alpha divided by 2 pi. So alpha, the angle of the sector, divided by the full angle of the full circle, 2 pi, should be the same as the ratio of the area divided by the area of circle, by the area of the circle. But we already mentioned that that's A divided by, well, the area of the circle, that was here, A divided by pi r squared. So it follows that, so I'm going to copy our conclusions upstairs. So far we concluded that alpha over 2 pi, so the ratio of this angle of the sector divided by the full angle 2 pi, so that ratio is the same as the ratio of the area of the sector divided by the area of the full circle. So from here it follows that the area of the sector equals, well, transfer that upstairs, so it equals alpha times pi times r squared divided by 2 pi. Pi cancels, and you're left with alpha divided by 2 times r squared, which is exactly the formula that you see here. Now, please notice that alpha is measured in radians.